Continuing with classwork 3.5. Now we are condensing using all three log rules. So that means I'm looking at the fact that I have addition and subtraction between different logarithms, and I'm trying to bring this into one logarithm. The first thing you need to check is, well, actually the first thing you need to check is are all the bases the same? But I'm not going to be cruel and give you a different base. But from there, the first thing you're checking is whether the logarithm is multiplied by a number, like what you see right here. Because I cannot work with subtraction between two logarithms when there's a number in the way. Understand that with order of operations, this multiplication is happening before the subtraction happens. Because of that, I'm not ready to combine these two logarithms with subtraction. I can combine these two logarithms with addition because they have nothing multiplied in front of them, but I have to move this 6 inside the function first. That will turn that into log base 2 of, and I'll put parentheses, but they don't have to be there. And whatever is inside that logarithm is now to the power of 6. I will at the same time take the addition of these first two logarithms and turn that into one logarithm where the two insides are now multiplying inside one. And now if you step back and look what you have a subtraction of two logarithms. There is nothing outside of the individual logarithms, and I just realized that I made a silly error and wrote a 5 there for some reason. There we go. And so I can use the rule where subtraction of two logarithms turns into division inside one logarithm. You can choose to multiply these two factors together, but you do not have to do that. I will consider this done as soon as everything is inside that logarithm. And this is just a factored version of simplified, but if you wanted to expand this, that would be a different version of simplified. But this is good enough to end with. On number 6, I'm looking around at what I have. I'm first going to identify that I have addition between two logarithms. I have a subtraction with a number and a subtraction with a logarithm. Now, where I have a subtraction of just a number, I need that number to be written as a log base 2. So what you want to remember is whatever base you're trying to change that into, inside that base, put the same base number to the power of the number that you are trying to morph into a logarithm. Then the other thing you want to notice is you have a multiplication by 5 here outside the logarithm. And other than that, you have a logarithm not having something multiplied, another logarithm not having something multiplied, and another logarithm not having something multiplied. So I'm going to focus on that 5 needs to become an exponent before that particular logarithm can join the bunch and condense with them. And so inside the logarithm, I have x to the power of 5. Now I'm going to, at the same time, take these two logarithms that are being added and don't have anything extra multiplying, and I'm going to condense them into one logarithm with multiplication. And then that takes care of that addition. Right after that addition is a subtraction of what was changed to log base 2 of 2 cubed. And by the way, 2 cubed is 8. And at this point, I can factor the negative, the subtraction, from both of these logarithms so that it becomes log base 2 of what I already have condensed minus the first logarithm has an 8 inside. The second one being subtracted, I'm factoring the negative out of both logarithms. So now I'm adding these two logarithms. And when I'm adding the logarithms, they can condense by multiplication. And if you can condense faster than the steps I'm taking, that is fine. You can go ahead and condense faster. And now all I have is a subtraction of two logarithms, and nothing is multiplied outside those logarithms. It is ready for a final rule of dividing what is inside. And again, you can choose to multiply the binomials in the numerator, but you do not have to because this is a simplified version in factored form. If you multiply them, that's okay because that is a simplified version in expanded form. And then we're going to take a look at the graph of the cube root of x. And a couple days ago, we looked at the graph of x cubed. So make sure you know that this is the inverse of y equals x cubed. Actually, I'm going to put that in blue to match the graph that I'm going to draw. I am going to draw, and I want you to see if you remember and can draw on your own, the graph of y equals x cubed. It goes through 0, 0, 1, 1, -1, -1. It's flat in the middle, and then it goes steeply up. I can even plot an extra point. 2 cubed is 8 to help me get a better drawing. Now, to try to get a better drawing. And then again, flat in the middle, and then very steep. And I can plot the point -2. When -2 is cubed, it is -8. So this is the graph of y equals x cubed that we already know. We're going to use this graph to help us graph its inverse function. Because the inverses are reflections over the line y equals x. So first you sketch the graph of y equals x cubed. Then I want you to draw a dashed line for the line of reflection, y equals x. And I'm going to see if I can draw a line. And let's see if the program will draw what I want it to draw. Okay, and then I'm going to change the color. It won't let me change the color, but I will change it to a dashed if it will let me. Or just do this, change color, try again. Okay. Yeah, that's still not fantastic. So I'll just delete it. When you do draw the line y equals x, it's very important that you notice that line goes through the point 0, 0, it goes through the point 1, 1, and it goes through the point negative 1, negative 1. Those are points that are shared by x cubed and the cube root of x. So there's that dashed line y equals x. And you can either use a visual look at the graph to try to draw the cube root of x, or you can help yourself by using a table. Cube root is backward on cubing, so if the answer to cube rooting is negative 3, then x was negative 3 cubed, which is negative 27, and we're not going to see that point. If negative 2 is the answer to x cubed, then x was negative 2 cubed, which is negative 8. And then for negative 1 multiplies 3 times to make negative 1. For 0, 0. And then the rest of the graph. So I can plot these 3 points that are shared by both the y equals x cubed and the cube root of x. I can additionally plot another pair of points with my cube root to try to get a good feel for where it's located. So I'm going to plot 8, 2, and negative 8, negative 2. Now this is really important. The x cubed graph was very flat in the middle. That means the cube root is very steep in the middle. And it's steep, and then it just kind of stretches out to the right instead of stretching up like the x cubed graph. And then again, the center is very, very steep, and then it begins to flatten and trying to go through this point. And you can see that it is reaching out to the left to mirror the x cubed graph reaching downward. And I do have on the answers to the classwork a nice computer-generated graph. Wonderful thing about these graphs, their domain and range is all real numbers. And you might recall that I told you about an inflection point being a point where the graph changes from a sad face to a happy face look, or vice versa. When it was the x cubed graph, it was a sad face and a happy face. So that made the point at 0, 0 a point of inflection. For the cube root graph, let me draw an axis, and then for the cube root graph, I want you to notice that this is a bit of a frown if you're looking at a frown on the left side. But over here, it's actually part of a smile if you're looking at the right side of a smile. And that makes the origin, or where the graph goes through the origin, a point of inflection as well. So the inflection point is 0, 0, and that's like a center of the graph, and it's a nice point to move from. So what you're going to be doing is starting off with the parent graph of y equals the cube root of x. I recommend that you plot these 3 points, 0, 0, 1, 1, negative 1, negative 1, but also plot 8, 2, and negative 8, negative 2, so that you have the graph going more sideways. Don't forget it's very vertical in the middle. And then do your best sketching, very steep in the middle, if you prefer to use that word. And we've got a basic graph of cube root. In part B, we are taking that parent graph and multiplying by 3. So that means the y values that I see, the y value 1 and the y value negative 1, 2, and negative 2. Those were the specific y values that we have. So I'm going to circle those numbers. Those numbers are being multiplied by 3. So when the graph was having a y-coordinate 1, it now will have a y-coordinate 3. Where the graph had a y-coordinate 2, it will now have a y-coordinate of 2 times 3, 6. And then on the negative end, negative 1 times 3 is negative 3. Negative 2 times 3 is negative 6. Where the graph is at the origin, it has a y value of 0. Multiplying by 3, it is still 0. So that 1 point will not change. The x-coordinates are not being changed when I multiply outside the function by 3. It's their y-coordinates that are stretched. So where I have the point 1, 1, that stretches to 1, 3. Where I had the point negative 1, negative 1, that now stretches to negative 3 for its y-coordinate. Where I had y-coordinate 2 for x equals 8, it is now 6 for x equals 8. And then negative 8 is having its y stretched to negative 6. And then you want to draw something very steep in the middle. And it's heading sideways. Steep in the middle, heading sideways. The final graph is starting with the cube root of x, the parent, multiplied by 3, already done. And now all that's left is addition, subtraction. Inside the cube root, x is being subtracted by 2. That means I need to add 2 to all of my x's. Add to 2x values, which you know more as move it right 2. Outside the cube root is a subtraction of 4 that affects y, and it does that operation to y. So that means I will subtract 4 from all of my y values of the 3 times cube root x graph, which you know better as to shift it or translate it down 4 units. So I am going to take the origin. I'm going to start with the origin that is right here. And I'm going to do its movement. Right 2, down 4. And that is now where my point of inflection will be, and I am erasing the previous point. Then I'm going to take the point that is located at 1, 3. And I'm going to move it right 2, down 4. Right 2, down 4. And I'm going to erase the point that was moved so I don't mix it up. I also have the point that was negative 1, negative 3, starting there. and I am moving it again, right 2, down 4. 4. There we go. And I'm going to erase the point that I moved. And I can also shift the other points. So I'm going to do that over here. This point is going to move right 2, down 4. And so that's going to put it at 10, 2. And then this point also moves right 2, down 4. And now I'm going to plot that at -6, -10. And then remember where your center is. That is really, really important. And the graph is very vertical there. It's very steep. And then it opens toward the right and very steep, opening towards the left. And let me show you the answers. Nicely drawn out. And there you go.